Hello my friends, today I'm going to look at symmetrical fault analysis, few examples, just 3 examples to study, and thereafter we'll look at other examples that will depend on the per unit analysis. These examples are going to be focused mainly on the equivalent reactance method.
Every single day I'm gonna make something great. That's my way.
The first example that we look at is the example displayed here. So here we're saying in this figure there's a single line diagram of a three-phase system. The percentage reactance of each generator is based on its own capacity. This implies that it's based on this capacity, which is 30%, and that 50% for each generator. And you are to find the short circuit current that will flow into a complete three-phase short circuit at point F, which is denoted here. So how do we handle this case? First of all, we have to select and choose a base kVA rating that we are going to adopt and use. In this case, we are going to adopt a base kVA of, let's say, 35,000 kVA as our base kVA, and then based on this base we convert all the variables that we have. For instance, in the generators or the alternators, we have said that we have the reactances provided as 30% and 50%. So we have to convert those reactances. So we take this generator or alternator A and alternator B and convert their reactances into the base reactance, and thereafter we calculate the line current in the 12 kilovolt line, and we go about it as follows. So the percentage reactance that we get for alternator A at base kVA is going to be equal to the base kVA over the actual rating of the system multiplied by the percentage reactance that is provided by the system. So in this case, what we get is the base kVA is 35,000, and we divide that by the rating of alternator A, which is at 15,000, and we multiply this by 30%, which gives us 70%. So that is our converted reactance or at base kVA. And thereafter we look at reactance of the second alternator, which is alternator B, which has a base kVA of taking 35 as our selected base kVA, and we have 20,000 as the actual kVA rating of that generator. This multiplies by the 50% and we obtain about 87.5%. After we are done converting these reactances to the base reactance, then we have to now calculate the line current corresponding to the base kVA rating, which we've chosen as 35,000 kVA rating. So our current therefore is going to be equal to the chosen base kVA rating, which is 35,000. This will multiply by 1,000 over because we're taking it as a per phase analysis, so we take this as multiplied by root 3, 12 kV, which is the voltage rating, multiplied by 1,000, and then we get our current to be 1,683.94 amps. So having done calculated that current, we now need to generate or draw a reactance diagram that is going to assist us to be able to define or calculate the short circuit current. To be able to do that, then our reactance diagram coming from what we have, if you remember, we've got a generator, we've got two generators that are connected through the bus bar, and then we've got a fault that is in the feeder as shown. So in this case, this is our A and B. We can then change or create what we call the reactance diagram, meaning that we've got the reactance from generator A and the reactance from generator B, and this connects together and meets at point F. So this is the reactance which we calculated at B. We had calculated it at 87.5%, and we've got the reactance here at A, which we had calculated at 70%. Knowing the value, we've already calculated the value for the current, so we have to now determine the total reactance between these two alternators. Now you notice that these two alternators are in parallel, so our total reactance is calculated in a similar fashion as we calculate the total resistance if the resistances are in parallel. So the total reactance here is going to be XA multiplied by XB over XA plus XB, and this is going to give us 70 multiplied by 87.5 over 70 plus 87.5. This leads us to 38.89%. And the short circuit current, therefore, is obtained from the line current corresponding to the base current multiplied by 100 over the percentage reactance, which in this case is that total percentage reactance. So we've got the current 1684.94. This multiplies by 100 over 38.89%. And this gives us the current solution to be 4330.16 amps. If we go back here, our solution for our short circuit current is equal to 4330.16 amps. Example number 2. In this question, the question says a 3-phase 30 MVA, the 3 kV alternator has internal reactance of 4% and negligible resistance. Find the external reactance per phase to be connected in series with the alternator so that steady current on short circuit does not exceed 10 times the full load current. To handle this question, we are going to do some calculations. First of all, we know that the percentage reactance can be obtained from the current multiplied by the percentage reactance, which is in ohms, over the voltage multiplied by 100%. Now, what we want to do is let the X in ohms be the external reactance per phase required. So this is the external reactance per phase required. Now let us we'll need to find the current, the voltage, and the required percentage reactance. Okay, so the current in this case is going to be equal to, we've got a 30 MVA rating, so we have 30 by 10 power 6 over, we've got root 3 by 33 kV by 1000, which is 10 to the power 3. Okay, and this gives us 524.86 amps. And then we also find the voltage to be equal to, this is 33,000, or 10 power 3 over root 3. This gives us the per phase voltage, which is 19,052.6 volts. Now, because the short circuit current is to be 10 times the full load current, our total percentage reactance required should be equal to the full load current over the short circuit current multiplied by 100. Now we are being told that the short circuit current is to be 10 times the full load current. This implies that we've got the short circuit current should be 10 times the full load current. So it's the ratio of 1 to 10 multiplied by 100, and this gives us 10%. Having obtained the total required reactance, therefore the external reactance that we require, external percentage reactance, is going to be subtracted from the total reactance. So we've got the total is given as 10, we've calculated as 10%. This subtracts the 4 that is provided in the question, which is this 4 provided in the question here, and that is a 4%, and we get 6% as the external required reactance. From there, we go back to our equation. So we go back to this equation to be able to calculate now what X in ohms would be. So we convert this equation to X in ohms to obtain the required solution. So what we are saying is that the required, the external reactance, which we've obtained as 6, is equal to I multiplied by X, that is in ohms, over the voltage multiplied by 100. This leads us to, when we convert the equation to the ohms, the reactance in ohms to be the subject of the formula, then we have X in ohms, which gives us 6 multiplied by the voltage over current multiplied by 100. And this gives us 6 multiplied by the voltage we had calculated as 19052.6 over the current, which was 524.86 multiplied by 100. And this gives us 2.178 ohms. Required X here in ohms is equal to 2.178 ohms. The third question that we are going to look at says a three-phase transmission line operating at 33 kilovolts and having a resistance of 5 ohms and reactance of 20 ohms is connected to the generating station through a 15,000 kVA step-up transformer. Connected to the bus bar are two alternators, one of 10,000 kVA with 10% reactance and another of 5,000 kVA with 7.5% reactance. You are to calculate the short circuit kVA fed to the symmetrical fault between phases if it occurs, 1, at the load end of the transmission line, and 2, at the high voltage terminals of the transformer. How do we get to the solution for this? First of all, like we said, we have to draw the single line diagram that positions or gives us an idea of what we are dealing with. So we've got two generators that are connected in parallel, and these generators are then connected through a transformer. Then we've got the line which has a reactance and resistance before it reaches the load. Now we're being told, 1, you've got a fault F1 just at the end of the line, and then you've got a fault at the high voltage side of the transformer, which we are going to call fault number 2. And we know the transformer is 15,000 kVA rating. You've got the generator here is 10,000 kVA, the first one with 10% reactance. The second one is 5,000 kVA with 7.5 reactance. Then you are given the reactance, the value of the inductance there, and you've also been given the value of the resistance. We take 10,000 kVA as the base kVA, and from this we are able to find now the percentage reactance at base kVA rating. So we start with the alternators. So we've got, if we label this as A and B, we've got the alternators, that is percentage reactance of alternator A at base kVA is going to be equal to the base kVA, which is 10,000, over the actual rating of that generator multiplied by its percentage reactance, which is 10%. And this gives us 10%. Then we go to the percentage reactance of the second alternator. We have the base kVA of 10,000 over 5,000 multiplied by 7.5. So this basically 2 by that gives us 15%. Afterwards, we now go to finding the line reactance in ohms, which must be converted to the percentage reactance as well. So when you get to the line, we have the percentage reactance of the line equal to, we're converting the percentage reactance from ohms to percentage reactance. So we've got the base kVA multiplied by reactance in ohms over 10 times the kV squared. So this is the formula that we use for converting to percentage reactance. And what we get here is we've got 10,000 multiplied by 20 ohms over 10 multiplied by the line is 33 kV squared. So this gives us 18.37%. And for the line resistance as well, we convert it to percentage resistance, which gives us the base kVA is 10,000 multiplied by the resistance is 5, 10, 33 squared. This gives us 4.6%. And thereafter, we now convert this diagram into a reactance and resistance diagram, since we've got a resistance in the line. So what we have is we've got the line reactance and the resistance before we reach Fort F1. So what we have here is you have 18.37%, 4.6%, you've got 10%, and you've got 15% as we calculated. So this is the neutral line. And up to Fort 1, now we look at what is involved, what reactances are involved up to the level of Fort 1. So for us to be able to find the short circuit current up to the Fort 1, we have to now find the total reactance, which is this reactance, and have a vector summation with the resistance. So in this case, we've got 10 and 15 in parallel connected to that in series. So the actual reactance here is seen is therefore equal to 10 by 15, because they are in parallel, over 10 plus 15 plus 18.37, and this gives us 24.37%, whereas the resistive percentage resistance stays at 4.6%. And now for us to get the overall total reactance, this is going to be the vector sum of the percentage reactance squared plus the percentage resistance squared, and this will give us the total percentage reactance. So we get our total percentage reactance to be equal to 24.37 squared plus the resistance there is 4.6 squared, which leads us to obtain 24.8%. And now that we know the total up to the point F1, the Fort 1, therefore the short circuit up to point F1 is going to be equal to the base kVA rating multiplied by 100 over 24.8, and this gives us 40,322.5 kVA as the short circuit current. If we want to look at the fault up to point F2, So if we come to this phase diagram, we see that up to this point, the only reactance that we have is the reactance from the alternator. And this is what we are going to consider. So to come to finding the reactance there, then we only look at the reactance from the alternator. In this case, the reactances, total reactance is going to be only the reactances from the alternator, which is 10 by 15 over 10 plus 15, which gives us a total reactance of 6%. And this is what we use now in our short circuit calculation up to point number F2. And this is going to be 10,000 by 100 over 6%. And this gives us 166,666.67 kVA as our short circuit current up to fault point F2. Okay, so this is the solution that we get. So here we get our short circuit current to be equal to 40,322.5 kVA, whereas here we get 166,666.67 kVA as the short circuit current up to point F2. This is short circuit current up to point F1. Thank you for listening. Thank you for watching these calculations. Subscribe for more. Thank you. Good day. My dear friends, thank you for watching this channel. Subscribe to the channel for more. Thank you. Have a good day.